This media was gratuitously produced by Clear Contributions Audio Video. The intellectual property contained within belongs to Dr. Barbara Van Kuyken. Clear Contributions. Let's have clarity.
So to recap, when you react a pi bond and you're creating something with an incomplete valence shell, then you're looking for electron resources. It might be neighboring bonds or non-bonded pairs. Now you know that if what you're reacting with has non-bonded electron pairs, it could share those, and so watch for that. If it does share it, it's going to form a strained ring. And today we'll go over how to resolve that issue. But in all the reactions that we did in Chapter 6, you were reacting with hydrogen in the first step, which doesn't have a non-bonded electron pair. So it can't do anything except watch in horror as a carbocation is created, and it's just, it can't do anything about it. But if you have something that has an electron pair on it, like chlorine, then that could react and use the electron pair temporarily to form a strained ring. So I think we'd gone over in B, but just to refresh your memory in case we did. You're still watching for where the carbocation would start to develop. The tertiary would be the correct carbon, and so that's where the electrons go from the chlorine to stabilize the developing carbocation, and that's how you do the arrows. H, you wouldn't have a reaction at all because the double bond is electron rich, and the hydride ion with the electron pair and the negative charge is electron rich, so you don't have anything electron deficient to go to, and so there's no reaction there. I'm just trying to make sure that you are thinking in terms of how things should pair up rather than just memorize stuff. Okay. Wait for it. If you're reacting with methanol and a trace of acid, then most of the molecules will just be methanol. You also will have a small proportion that has the hydrogen attached to the methanol. That's the one that could react because these bonds are too strong. And so the only electron deficient thing you have to react with is the hydrogen that's attached to the methanol so that the oxygen has a positive formal charge. Because it's hydrogen, it can't do anything about the developing carbocation, and so the carbocation just forms. So your product there is going to be with the hydrogen attached here and the carbocation there. Okay, then I don't want to confuse the issue here. We'll do one step at a time. With mercury, you have the option for electron pairs. And so as the carbocation starts to develop on the tertiary carbon, right here, the mercury can share the electron pair, and it will also form a strained ring. Just like before, you're sending the electrons to the tertiary carbon because that's where the carbocation is going to start to develop. And mercury would have too many bonds, so you let go of one of the OACs. Great question. I must have shown the afternoon group and not you guys. I remembered showing it to somebody and I guess it wasn't you. So that's acetate. And if you remember from Chem, C2H3O2, the structure for it is actually that. And you're attached through the oxygen, and that's why it has the O. But AC stands for acetate. Yeah, the carbocation that's developing, because that's the resource you're getting electrons to it. So now this chapter makes me a little bitter because the resources that you're using here are going to be things that you would do in an OChem lab. And so really it isn't terribly practical for you. And for a physiology class or something, the way that chapter 6 was, where you're trying to figure out how to deal with a carbocation. But these kinds of reactions are what you might see on a standardized test. So even though you're not going to become organic chemists, you're going to want to know this little trick anyway. So the reason why you use this in an organic chemistry lab is because it doesn't allow a shift because you never have a carbocation there. And so if you wanted to run a reaction and prevent a shift from occurring, you would use something like this. Okay, so now we'll finish the reaction. So when you have a cyclic ion like that, and these are going to be ions, and I was sloppy and I didn't put that in. I'll show you why. They're going to be ions, not why I was sloppy. Chlorine would want to have one bond normally because of where it is on the periodic chart. And so when you have it originally, it just has the one bond and it's happy. When you turn it into the cyclic compound, it now has two bonds. It has one more bond than it wanted. And so it has a positive formal charge. Same thing with the mercury, where it has a positive formal charge on the end when you form the intermediate. So that's called a cyclic ion intermediate. So the reason why it has to be resolved is because, why don't you want to leave it like that? It's a strained ring. You've got the bonds too close to each other and electrons repel each other, so they don't want to stay that close together.
Is there any natural compound that is in a 3 or 4 membered ring that is stable?
No, not really. Not that I can think of off the top of my head anyway. Okay, so we've got to take care of that issue. Just to reiterate, though, in your sequence of priorities, an incomplete valence shell was the worst, and then a strained ring. So that's why you went to this option of forming a strained ring rather than a carbocation, because it's better. But it's only marginally better because this is still crazy reactive. So with a carbocation, you know how it's so crazy reactive that it will react with anything that has a non-bonded electron pair that it runs into, because that will fix the situation. Same thing here. It will react with whatever it runs into as a non-bonded electron pair that can add electrons to the tertiary carbon, so the tertiary carbon can let go of its bond to the halogen or mercury. And so the main criteria when you're looking for the best nucleophile is the highest concentration, because that's the one it's most likely to run into. It's so reactive, it's not very selective, so it's just whatever it runs into first. So concentration will be the big factor there. So you're looking for a high concentration, and of course it has to have a non-bonded electron pair because that's the only way that you can form the bond. But that's what's making it a nucleophile, is it wants to share electrons anyway, so that kind of goes without saying. But so you're looking for the highest concentration. So if I'm going back here, for instance, to E, how would you choose which carbon you're going to react with?
It's the one that was going to be a carbocation, right?
Mm-hmm. The tertiary carbon is going to be the one that would have been the carbocation. It's also the one that's more reactive. It has less claim to the bond, or that bond is weaker there because it's kind of a little bit more stable as a carbocation. So that bond will be easiest to let go of. And the other thing is you start to kind of develop a carbocation as you're reacting with a nucleophile because the carbon has to let go of its bond to mercury or to halogen. So it's still the same issue as before. You're going to go with the one that would have been the better carbocation or forms the better developing carbocation. So now, this is where we kind of run into a style issue. The example above that looks like this. And I said that you're going to be reacting with this carbon since it's tertiary. Usually if I go something like this and react it from that side, everybody freaks out and goes, well, but there's a methyl group there. You can't do that. And so, starts to have an issue. The molecule doesn't actually look like that. Doesn't look like that either. It's like you have this is in a plane, and then you have the mercury blocking it from below. But you can react this nucleophile with either carbon. So since we want to go with the tertiary, that's wide open. So the difference is whether you want to draw it the way it actually looks or the simplified way that we've been doing it. If you decide to draw it the way it looks, all you got to do, you could even draw it like this so that you can kind of picture what you got going on. But it's just like move these down so that they're in the same plane. If that helps you picture. And you can do that with any of the stuff that we've been drawing so far in this reactions section. Even chapter 6, where you have a carbocation or carbon radical, it's trigonal planar. And so you can always redraw it like that if it helps you picture better what's going on. That's what I asked you for advice yesterday on what would help you the best, to be able to do these reactions, because I know that this is a lot easier for you to picture how to draw it. This is harder, but in the end it kind of helps you picture what's going on. And I haven't settled on which way to draw things in the textbook or in class that will be the best for you. So work with both ways and give me feedback what's going to help you. All right, so the next exercise is referring to skills check 1, show the reactants and mechanism for the final resolution. I'm going to just put them on this same page here so I don't have to redraw the first step. And I got to make a whole lot more room for myself, so. I really, really like these iPads. I really like being able to draw things and copy them and move them around, and oh boy, this is great. Ta-da! Okay, so for the first one, that one you should know how to do by now. That one's pretty easy. You have a carbocation here. So step 3 is see if you can shift it into a better location. No. Step 4 is if it's still unstable. It is. Then list and label all the reactants, and that would be anything that was in excess from the first part or that you haven't, or that was created in the first part. So the only thing you got really here is the bromide ion, and so that's got non-bonded electrons. That's present in the highest concentration, so that adds on, and you just have the bromide on there. Yip-de-doo. Okay, but on B, where you have the strained ring, I'll show you how to resolve that. It's the same thing as before. You want something that's present in the highest concentration, and so you list and label all the stuff from before that's either present in excess or that you created as a result of the reaction. And so that's going to be the chloride ion is the only resource that you have here. So your features are that you have a strained ring in this reaction, and you also have a negative formal charge on the chloride. The thing that's driving the reaction is that crazy strained ring. So that's how you know that you're looking for something that has electrons that is present in the highest concentration. Once again, you react with the tertiary, the better developing carbocation, and it's not going to make a difference in the product this time, but it might in the future. Oh yeah, it will sometimes. So you still want to know that you're reacting with the tertiary carbon. What you're doing is supplying electrons to that carbon so that it can let go of its bond to the chloride and open up the strained ring. So this is like telling the little Dutch boy he can take his fingers out of the dike because you got somebody there with a spackle that can fill it in for reals. And don't be disturbed that I'm moving the methyl groups around. Remember, it doesn't show stereochemistry anyway, and the bonds can rotate and everything. So I'll just put the chlorine on the opposite side there for you so that it kind of looks like the way that I had it approach. The chlorine, by the way, or the chloride, I should say, by the way, has to add on from the opposite side because the chlorine that's part of the strained ring is blocking this whole side. So it has to add opposite. That'll be important if we get to the stereochemistry today. Well, it'll be important even if we get to stereochemistry on Monday, but I'm just saying. Okay with that? All right, and this one is just like what you've seen before, where you're going with the highest concentration, which would be the methanol. And so the oxygen is the source for electrons. Hopefully you're feeling bored with that whole reaction now. So that's your issue. Electrons go to the rescue, da-da-da, and drag everything with them. Oh dear. Although I'm creating mayhem. Okay. On E, once you've got the strained ring, you're looking at the resources that you have left over. Your resources are the acetate that came off, and it's got a negative formal charge because it took the electrons with it. And then you also have methanol, since you didn't react the methanol in the first step. In addition, methanol is present in high concentration since it's the solvent. And we'll cross off the carbon and hydrogen, put in the charges. There you go. So there are the things that you have to select from in this step. And to react with the strained ring, you used the high concentration methanol. Need the electrons from the oxygen, so it doesn't matter that the carbon or hydrogen are crossed off. We're not reacting those. Has to add from the opposite side. When it does, you let go of the bond to mercury.
Why? It has to attach the opposite side?
Yeah. It's because if you saw the carbons, well, in sort of the way that they look, and you've got the mercury is like this. It's blocking this whole side, but this side is open. So it has to add opposite. Just like before, since the methanol, the oxygen of the methanol would have a positive formal charge, you can drop off the hydrogen. That's fine. Okay, so that's the product that you have. And see, this time it was important to know that you're adding on to the tertiary carbon because that would have made a difference in the product. So I'm going to take the hydrogen off. That's what you got.
Dutch ever consider just moving away from where we live?
No. Never.
Places that they won't die at in water
No.
that never crossed their mind?
No. See, I think of it as them being so ingenious. Who else sat and pumped out their country? Okay, now, normally you're not going to create a molecule that you want to have mercury attached to it. Yeah, so with the reactions with mercury, you're going to see something like this on the reaction arrow. You'll see in the first step that you're reacting it with mercuric acetate, and you got the water or methanol or whatever. And then they'll have a second step. And that means after this part of the reaction is all done, you wait and you let it cook and do whatever. After you got to this point, then you add another ingredient to get the mercury off. And that's sodium borohydride. And I'll show you why you use that and what it does and how you can think about it. So you know how boron is a moron. And so it wants 4 bonds. No, wait, then it has a negative formal charge. It really wants 3. No, wait, then it doesn't have a complete octet. Now, maybe it wants 4. No, we're still back with the negative charge issue. No, 3, I'm not sure. Anyway, that's the deal, is it just kind of like can't decide. So you use that indecisiveness to your advantage in organic chemistry. So if you ever see boron with 3 bonds, you think, oh, it wants to form a new bond. If you ever see it with 4, you think, oh, it wants to get rid of one of them. And so that's what you got going on here. This is a ionic compound because you have sodium, a metal, with the borohydride, and so that's going to come apart in solution. So when it comes apart in solution, I'm sorry, I'm running out of room with everything here. You have the sodium as a cation, and then the borohydride anion. That's why you had to put the sodium in with it, because you have a negative formal charge on there. And the sodium has to be a counterbalance ion. Anyway, you know how in chapter 5 I was telling you that a group 1A ion is not going to do anything. It's happy the way it is. It lost an electron so it could have a complete valence shell. It's not going to react to gain electrons or lose them. And so you're always crossing that off. So instead, you're focusing on the BH4. Boron the moron, oh my gosh, it has 4 bonds. It wants to get rid of one of the bonds. So it lets go of a hydride. The electrons from the bond go to the hydrogen because hydrogen's more electronegative than the boron. And plus, the boron is kind of like, oh, I got too many bonds. I won't let go of one of them. I'll give it to somebody else. So that creates a hydride ion. So anytime you see NaBH4, you can just redraw it in your list of reactants as the hydride ion right here. That's the whole goal of what you're putting it in there for.
More partially negative?
More partially negative? Oh, for the electronegativity? Yeah. No.
Wow.
No, hydrogen is right in between boron and carbon in terms of electronegativity. Yeah. Okay, so at any rate, when you see the sodium borohydride in step 2, it means you create this monster, and then in your next round, you got like this hydride. What do you do with it? You add it on the carbon so the carbon can let go of the mercury. The whole point to that is to replace the mercury with hydrogen. Another thing that you could do, I suppose, is Hg becomes hydrogen if you just erase that G. Oh, look it. It's a reaction mechanism. No, I'm kidding. Okay, so I'm sorry for all the crazy drawing there, but that's found, that information is found in chapter 5. It's just we haven't used it, and so that was 2 chapters ago, so it's a little muddy for you. But if you've forgotten, you can always go back and look up sodium borohydride in chapter 5. So the last thing I want to go over today is stereochemistry for these kinds of reactions so that you can practice these kinds of reactions as a complete set. Remember, you're doing this little triangle dealio when you have anything that has a non-bond electron pair that could add on to the pi bond, but specifically the most common examples would be mercury or a halogen. Okay, stereochemistry. It's not quite as easy as it was in the last chapter. We're not doing a pi complex today. Okay, stereochemistry. So in the last chapter, and I'm on page, I'm sorry, I forgot to tell you what page I'm on, 10. In the last chapter, we said that the alkene, the vinylic carbons of the alkene, are trigonal planar, so you can add to either side, so that's Rs. And the carbocation or carbon radical you create is trigonal planar, so you could add to either side, so that's R and S. So if you have one chirality center, it's R and S. If you have 2 chirality centers, they're both RS combinations, and so you got all 4 possibilities. This is a little bit more complicated, though, Because yes, you could add to either side in the first step, but once you add that strained ring, now you limit what you can do in the second step. So you're only going to have two possibilities, and so it's going to be a little more complicated to figure out the stereochemistry when you have two chirality centers. So anyway, to work with this, first you need to know some definitions, because I'm going to be throwing those out to help you learn how to predict two chirality centers. So an anti-addition is where the first molecule, the electrophile, adds on one side or the other, but then it blocks that side so that the second part of the reaction you have to add from the opposite side. So that's what we're doing here with the little strained ring. That's a type of anti-addition. So that would be X stands for halogen. So anything with halogens or mercuric acetate. I have one more type of reaction to show you in this chapter, but I'm not going to do that today because it's just going to mix in with everything else in your head and get kind of jumbly. But that one is going to be syn addition, and the definition for syn addition is that the second molecule has to add from the same side that the first molecule did. And that's because they're coming from the same molecule. So they have to add to the same side. That would be a syn addition. I'll show you the example on Monday. Don't worry about it for today. It always works better when you have an example. Okay, so these are all examples of anti-addition. Okay, if the reaction has a syn or anti mechanism to it, and you create one chirality center, then once again it's 50-50 RNS. So it doesn't matter what the mechanism is, carbocation, carbon radical, syn, anti. If you're creating one chirality center, it's 50-50 RNS. The reason is because when you start out with the trigonal planar vinylic carbons, you could add to either side, even if it's a syn or anti mechanism. So that part's easy. It's when you have two chirality centers that you're creating that it could be kind of tricky. So I'm putting side-by-side comparisons with Chapter 6 and Chapter 7 with what your situation is. If you have one chirality center, it doesn't matter if it's syn or anti, 50-50 RNS, or the next question is carbocation or carbon radical, 50-50 RNS. It's also known as a racemic mixture. I haven't used that term for a while, so I just want to throw that out there, refresh your memory, that you might also see it that way. Okay, now if it's a syn or anti mechanism and you create two chirality centers, this memory device will be probably the most helpful way for you to go because it's going to be hard to picture the stereochemistry. You use the predictive device cis, syn, erythro. And what it means is if you start out with an alkene that has the same high priority things on the same side, and you have a reaction mechanism where you're adding things to the same side, then the product is going to be structured, the Fisher projection of it would have the same groups on the same side. That's erythro. Remember, that's where you have the groups on the same side, kind of like a letter E. So this is really same, same, same. Start out with the same kind of alkene and add things to the same side. You're going to have them on the same side in the end. So the only thing that you need to know to work with this is if you have to change something, like for instance, let's say that you start with an E alkene where things are opposite, then that would change something else, right? Because you've changed conditions. So if you change this, but this is still syn, then that has to change. It has to be the opposite. Or if you start out with something E, and you have an anti-mechanism, then you changed it and then you changed it back, so that stays the same. So it's kind of like math class when you're multiplying negatives together, then they become a positive if you have two negatives. So it's kind of like if you change one thing here, you have to change a second thing to switch it back to compensate. So you either change nothing or you change two. This is going to be set by the directions for what kind of alkene you're starting with. This is going to be set by the type of thing that you're reacting the alkene with. And the reason why you're going to create an erythro pair or a thrio pair is that you're going to create a pair because you can add to either side in the first step because that's trigonoplanar. But once you do, you locked into what you can do in the second step. So you're only going to come up with 2 stereochemistries in the end. So you're going to have 2 because you can start with by adding to either side, but you're only going to have 2 because then you limit yourself in the next part. So I've got a whole bunch of examples for you where we're just going to work with a stereochemistry, predicting stereochemistry, and then we'll put it all together into one problem, I hope. Okay. And as a refresher, if the product has a carbocation or carbon radical intermediate and you create 2 chirality centers, then you got 4 possibilities because it was trigonoplanar in each step. That's a whole lot of new information for today. So to recap, once you form the strained ring, look for the highest concentration, react with the carbon that would have been the better carbocation. And then if you have 2 chirality centers, you're going to use cis syn erythro to try and predict. You only use that, though, if it's a syn or anti mechanism. Okay. Okay, so I'm going to have you jump down to page 14. To work the skills check problems, so you can see how it applies. If an alkene reactant has a Z configuration and 1 chirality center is created and you have a syn mechanism, what's the stereochemistry going to be of the product? It's RNS because you have 1 chirality center. So it was kind of, didn't even matter that it's a syn mechanism. Okay, you start out with an alkene that has a Z configuration. You create 2 chirality centers. It's a radical mechanism. For a double check for everybody, what do you think it is?
R.
RR, RS, SR, SS, because it's a radical mechanism. Radical or carbocation, trigonal planar, so you get all four possibilities. Okay. The alkene reactant has an E configuration. 2 chirality centers are created, and you have an anti-mechanism. Because this says you have an anti or syn mechanism, then that means you're going to use cis and erythro. Okay. No, because you have 2 chirality centers. Yeah, so you start out with cis and erythro, and you cross off anything that doesn't match, and you make sure that you have either nothing crossed off or 2. So it has an E configuration. That means we're changing Z to E. And then it says that it uses an anti-mechanism, so you're crossing off syn and changing it to anti. Since you've already changed 2 things, that means that you've switched up what the stereochemistry would be, and then kind of put it back again because you changed something else. And so that would be a pair of erythro.
So
Okay,
you crossed out 2 things because there are 2 chirality centers being created.
No, I crossed out 2 things because it says that the alkene reactant has an E configuration, and you always go cis, syn, erythro. And then if something matches, you don't cross it off, but if it's different, then you do. So it's not Z, it's E, so I had to cross that off and write the E in there. And then it's not a syn mechanism, it's an anti-mechanism, so I had to cross out syn. And since I crossed out 2 things, then that means that's all the more.
Oh, okay, so the E and the anti are provided in the question.
That's right. And don't worry about the fact on D that I've got the I circled, because that's just a typo. And I've just circled it for myself. The alkene reactant has an E configuration. 1 chirality center is created. The reaction has a carbocation intermediate. What's the stereochemistry going to be? RS. You have 1 chirality center. You don't even have to worry about the type of. Okay. Alkene reactant has a Z configuration. 2 chirality centers are created. That's when the mechanism becomes important, and it uses an anti-mechanism. Uh-huh. It's 3, that's right. You either cross out nothing or you cross out 2. The Z stayed the same, because that was how you were told the reactant was. And then it's an anti-mechanism, so I had to cross out syn and replace it with anti. So now I've crossed something out. I got to cross out something else. Can't cross out the reactant, so I got to cross out with the stereochemistry as the product.
Why do you need to cross out 2 things?
Because if I've changed conditions, that makes the stereochemistry opposite. So the fact that I've started out with cis, but now instead of it being a syn mechanism, it's anti, that means that the stereochemistry is also going to be opposite.
You don't cross out cis because it's a Z.
That's right. All right, and the last 2 are about cyclic alkenes, so we're not going to worry about that just yet. I'll show you those next time, since we're out of time. All right, I think I've got homework back here. Just a minute. I don't want to send you out the door without homework, just because I think you need to kind of get this down, and just having you let it settle for the night is not going to do it. Just a minute. I've got something back here I think that'll work. Aha! On page 48. That's your homework. It's the same kind of thing that we were just doing, just to make sure you can predict stereochemistry just by itself.
Is it question 8 or just 8?
Question 8. The whole thing of question 8, so that's 48 and 49.